All right, so we're continuing on with class 20, and in the end of the last video we talked a little bit about entropy as a property that we can look up in tables and in figures, and we introduced the TS diagram, which is important to us. We can look up in tables, we can find, knowing the quality of a mixture, if that's what we happen to do, we can find out here if it's superheated. We can look up in tables to find it, the superheated properties. If it's a compressed liquid, we could actually pretty much just know that we're going to be on the saturated liquid, so SF is going to be good enough for us for a compressed liquid. Here is the TS diagram. I think is the TS diagram. It's in the figure E1, temperature entropy diagram for water. You can see the vapor dome kind of in here. These have lines of constant things. Like here's a line of constant temperature coming along. But of course, this is the temperature scale over here on the right. The entropy scale. They have a little weird. They went joules per gram degree Kelvin. Well, of course, kilojoules and kilograms. So that works out to the same value. So the straight up and down is isentropic. Oh, I think I had one of these labeled wrong. I forget which one it was. Oh yeah, the constant quality right here. I accidentally, I didn't put the specific volume in there, so I mislabeled that. Constant volume should be this light blue right there. So you have to look on this diagram. You have to look for where they have the thing written, and then look for not really parallel lines, but lines that go in the same kind of sense to them, and look what the value is, and start to climb up on them. Make sure you get the right units. So like this one is centimeters. It should be centimeters cubed per gram. It's a little weird. You have to kind of work that one out. Constant enthalpy is right along here. Constant temperature and constant pressure are the same underneath the vapor dome, but then outside the vapor dome, the pressure, constant lines of pressure are like right along there. So good things to note. Here's another one from Sengel. Interesting diagram. A little easier to read, I think. Still, you got to look kind of pretty close to be able to figure out what they are. I guess maybe the units kind of help on some of them to be able to figure out where these lines are. Then, as I mentioned, here's the Moliere diagram. Here's one out of this is an excerpt out of the FE equation book. So you can see that it's important enough to be included in the FE equation book. It's important enough to be included in this class. And then his is out of Sengel. Give it kind of a prettier look to them. All right, so here we are. This is the meat of what we were talking about in this video. I'm talking about entropy and change in a reversible processes, and we'll start out with the Carnot cycle. Carnot is the best that we can do, and the highest efficiency that's possible. It's made up of four reversible processes. I think one on the left is an engine, and the one on the right is a refrigerator. So we start up here where we, at high temperature, we add heat in between 1 and 2. And then we extract out work in isentropic process, so it goes straight up and down. And then we take heat out. We're removing heat right here. And then we're putting some work back in, and we go through a cycle. Let's see, I'll go back to the camera, I guess. And so we could say when we're right here, this process, this is the work out, right there. But we recall that we have Q in. Well, they're showing this as H right here, but that H should apply to this whole thing right there. So we'll go like Q in, or which is QH for us, is going to be equal to, and let's start 1 to 2. So how we want to do it? Yeah, 1 to 2, and because we want to get the area, and we're going to go 2 to B, so all the way down. So the area underneath here, right? It's because we're going to have well, they didn't really quite show it right here. I'm going to say that looking right in here, so we have that and that. So we're going to have that Q3, 4 is equal to T, which is going to be, okay, I guess I'll go for the L one right here, times S4 minus S3. And that's the area. Right here, this is the area under the curve, right? So this is the area, that's the one, I should have finished this thought right here. Let's do this one to come back to it. So the Q out is the QL right here. And that's going to be 3 to 4. Did I write it that way? Yeah. 3 to 4, here to here, to A, so down here, to B, to 3, right? So this is the rectangle that's described right there, right? We go down to there, and that area in there is going to be found by taking this TL, which is right here, and multiplying it by this width, right? So we have, here's the here is the height, right? TL of this rectangle, and you set this right here, 4 to 3, there to there, is the width of it. So we have height times width, so we have area right in there. Similarly, for the entire thing in, we go from 1 to 2, and then from 2 to B, and then from B to A, and then from A to 1. Did I do that right? Sure. And we recall that we had that the work would be, and did I write this underneath it? I didn't write it underneath on mine. That this right up here would be TH times S2 minus S1, right? So that's QH is going to be, or we could go Q, I guess 1 to 2 is going to be TH S2 minus S1, right? And that the work is going to be equal to QH minus QL. So as an efficiency, right, we have what we want, net work, divided by QH. So let's take a look at what the work is. The work is going to be 1 to 2, 2 to 3, 3 to 4, 4 to 1. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. That's what that describes, right? So that's this guy right up here. That's the thing that we want. And we define that by this QH right here. So that's 1 to 2, 2 to B, B to A, and A to 1. Right here. So that big rectangle, the biggest rectangle, this small rectangle, this part that's useful to us, divided by the big rectangle, which is all the heat that we put into it. And of course, we're going to reject the rest of the heat. Note that this becomes the Carnot right here. So it's really, we end up having a temperature relationship between here, that this was TH minus TL over TH, and that we also found that algebra gives us TL over TH. So just recall. And that's what we had. That's the important thing. If we want to take a look over this guy right here, this is a refrigerator where we're taking the low temperature and we're placing it into the thing, and we're rejecting out high temperature, and we're doing that by way of putting work. We could also say this is also the heat pump, if we will. And so if we're going to do the same thing right here, remember that we have the coefficient of performance for a refrigerator is that we call it beta in this book, that we're going to take the area, which is going to be, let's see, let's go back up to here. It's going to be 1 to 2, right, because we're going in that direction, 1 to 2. And then, I should, sorry. Remember that by definition was QL divided by the work in. And so this is the area of the QL right here, 1 to 2, 2 to B, B to A, and A to 1. So 1 to 2, 2 to B, B to A, B to 1. All right, so that's that guy right there. And by the work, which is going to be the area that we put into this thing, which is the stuff inside here, right? So inside the little blue section, there's a blue tint to it. So that's going to be 1 to 2, 1 to 2, but then 2 to 3, and then 3 to 4, and then 4 to 1. And then if you're going to do it the other way around here, although the coefficient of performance for a heat pump was beta prime, which is now going to be the QH over W, right? So that's going to be this whole thing, right? Let's make cross hatches going that way. So the QH of the whole thing is what we're extracting, and we're using work to do it. So we have the area of 3 to 4. So up here, there to there. And then 4 to A. So all the way down. There's A. Get kind of covered up by all this mess I'm putting on top of it. And then A to B. And then B back up to 3. Well, B. What did I do? Yeah, B to 3. Right? Boom. So we're going to go 4, boom, 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 boom. I guess I could have gone a different direction. No, I started here. Boom, 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 boom. Okay. So that's the heat that we've extracted out, and they're going to be able to use, or we're not extracted out. Well, I guess it is. We've extracted out, but we added work to it. Like we extracted out this heat from the outside world, but plus the work that we put into, like with the compressor, then the QH is what we put into the house, right? And so this is the area is 1 to 2, 3 to 4, and 4 to 1, just like it was up here and just like it was up there. So here is our Carnot cycle projected onto a TS diagram. We can do this, it's possible, to check out what happens by putting it into, using it as the medium or the working fluid to be water. And we could use it either in the vapor dome or across the vapor dome, as I've done in a homework problem with you. And notably, though, this would be for a constant pressure, as we're showing right there. That this part of it right here is not a reversible process. We could demonstrate that here in a second. But right here, here is an aspect where we do have inherently in a vapor dome, we have an isothermal process, right? So we had that. Here's an isentropic process, but here is an isothermal process right here, and that's useful to us. So we could say when looking at this, at least in this instance, right? It's not necessarily true all the time, but if you do have this process from 1 to 2, you could say that the heat flow that's coming from here to here is actually going to be equal to the enthalpy change in between the fluid and the gas. So that's actually already in our tables right there. And so if we were to do this as a thought experiment right here, let's take a look and see what this would be for a given temperature, right? So let's go to, or pressure, right? Because the pressure and the temperature are both constant as we're going across. So for my example that I think I'm using out of the book too, by the way, we would see, we're going to use it for 10 megapascals. Yeah, 10 megapascals. We're going to check this out right here. but we could see that we're going to go. So the change of entropy between 2 and 1 right here is going to also going to be equal to SFG, which is by definition here is going to be Q1 to 2 over temperature, which we will hope to see that we have HFG over T, right? So this inherently, this is sort of like investigating the steam tables. So let me open up the steam tables here. No, I could just look in the book. I have the book open in front of me. This video is too long. But let's do it anyway. We can get onto some examples after this, I think. I hope so. I have it right here, so I don't know why I'm flipping around with thumbed off. So let's take a look at 10, by the pressure one right here. By pressure, I said it was 10 megapascals, which should be, is it 10,000? Yeah, it should be 10,000 right here. Okay, so the temperature should be 311. Let's see, let's get rid of this thing right here. I don't know why this. Okay, so we have 311, and there's we're on the specific volume page. So let's go over to the facing page right here under pressure, and we're going to look and find out what the enthalpy is, but underneath the vapor dome, right? The crossing horizontally across the vapor dome, we have this guy right here. So 1,317.1. So let's write that down. HFG, this is at 10 megapascals, is going to be equal to 1,317.1, and these are kilojoules per kilogram. Let's see what SFG is going to be equal to. So right up in here, and follow that down, and 10,000, we should have 2.2545. 2.2545, let's say. And these are kilojoules per kilogram. Degree Kelvin is their entropy designation. And so let's find out. Let's see what this equals. Let's see what this equals right here. So we're going to say S2 to 1. Oh, sorry. I didn't mean to designate it that way. Minus S1. Let's say that it's F right here, just like I said up here. So over temperature. So we have 1,317.1. And this is by Kelvin, right? So we better add 273 plus, this was a TSAT, should have written that down, of 311.06 degrees Celsius. So 311.06. So now it's in Kelvin. Divide this through, and we get 2.254. I didn't bother with another sig fig. Let's see what happens at the sig figs. Let's see how close it ends at 1317.1 and 311.06. 273. Of course, I think it's 273.17 or something, but I didn't bother, so maybe that'll account for some error. But sure enough, we get see, I don't want to lie to you, 2.2551, right? So you could see the interrelationship, at least some of it, between enthalpy, which is heat change in this context right here, and entropy change. It should be noted that this entropy change will really only work for reversible processes, which is true of an isothermal process right there. So all of this is to try to get you used to the concepts of entropy and of it as it being a property that could be useful to us in calculating the performance of thermodynamic processes and ultimately thermodynamic cycles.